Okay, what we're looking at here is acceleration of a falling mass attached to a rotating disc. So we'll just identify a few things. This is obviously the most important part of setting up your problem. That's just a frictionless pulley as usual. We'll identify the mass as mass. The disc, we'll give it a rotational inertia of I, which we all know is equal to mr squared divided by 2. Now, don't confuse the two m's. We're not actually going to be using this m in our calculations. We'll just leave I at the end of the day in our formula for the acceleration. So we've got mg acting here. That's our weight force. We've got a tension, I'll call it Ft, in the rope. It goes both ways. It's that tension which supplies the force, which supplies the torque to rotate the disc. We'll identify another force, the net force. So mg, or the tension force here, is going to be equal to mg minus F1. We've identified F1 as the net force. So A is also going to be equal to F1 divided by m. Net force divided by the mass will give the acceleration of the falling mass. Weight force minus net force will equal tension force, or the other way around, mg minus Ft will be equal to F1, or the weight force minus the tension force will equal F1. So I think we're ready to go. The first thing we need to think about is the fact that right here, the tension force is providing the torque that produces the acceleration. So we can write that down immediately as Ft, tension force, times radius, must be providing the acceleration, or the angular acceleration. Now the angular acceleration is, we can substitute in as well, remembering that alpha r equals a, so a over r equals alpha. So we can substitute there and put that as an a over an r. Now we could have the r squared, but first I'm going to substitute in the Ft. So the Ft is mg minus F1. mg minus F1 times r squared equals I alpha. Starting to look a bit better because we've got an acceleration, which is what we're after. So we can go mg big R squared minus F1 big R squared equals I alpha. Looks like we've got another substitution coming up with the F1. F1 is equal to AM from there. So we can go mg big R squared F1, which is AM, minus AM big R squared equals IA. Now what we're going to want to do, get the A's on both sides, right? That's always a sensible thing to do. So we can go mg big R squared is equal to big I times acceleration plus AM R squared. Take out the common factor of the A's, then we've got I plus M R squared, mg R squared, and we're starting to be there. So we can bring that over, and so A equals mg R squared, all divided by I plus M R squared. Now, don't make the mistake of substituting in the I, the m big R squared over 2, and then cancelling out m's and things like that, because that m is different from the falling mass m. This is the formula we wanted.